Frequency hoppers, that's how Bluetooth works. They're both at the same frequencies. Okay. All of you are all over the planet, and we all have to work with our local jurisdiction in what frequencies you can use. The thing where it's through a circle on is in the United States, it's the frequency allocation table. A moment ago, you just saw there's a lot of networking that comes in here. That's going to be at play. Inside the communication world, there are different ways to send a 1 and a 0. The easiest one is amplitude shift keying. If it's a 0, make it really low. If it's a 1, make it really loud. So it's an amplitude shift between sending 1s and 0s. Or maybe you want to stay at a constant amplitude, but you want to send a 0 at a certain frequency, and you want to send a 1 at another frequency. 0, 1, 0, 1. That is frequency shift keying, and that's how you can send your 0s and 1s with equal amplitude, but you're using frequency as the discerning or the delineating factor between the 1s and 0s. It's like AM and FM radio. You know, AM is great for long broadcasts, but it's prone to failure. It's prone to noise. And FM it's got a brick wall performance, and it works really well, and then it doesn't work at all. So it can come into play. On the left-hand side, this is what every field device looks like. Every field instrument, I don't care who the vendor is, looks like that. It's got a sensor, it's got an intelligent controller, a microcontroller inside it, it's got a power system, it's got some circuitry. Auxiliary circuitry would be like this little ASIC that's sitting right here doing something. If it's wireless, it's going to have an antenna and a radio. If it's wired, it's going to have just a cable coming out of it. But the rest of the stuff is all the same, and you'll see it. That's the common design it's the generic design for all instrumentation. And you'll walk through. You got a great speaker for this stuff. And that individual will walk through what the microcontrollers are and so on. It's kind of cool. Antennas and so on. Oh my goodness. Peter's gone back to Canada. And yes, I have again. So here is a 3D diagram of that mine, the Cameco uranium mine, because I know all of you can really resonate with this type of design. It's like, okay, I understand the iconography, I understand the graphics. You can see, as the Canadians would say, while they were eating their donuts, they would basically say, oh, this is where the money is, where they were really extracting the uranium. And so it's a wild idea that this is the structure. So you go in there, you extract the uranium, and you have all the pieces, and this is also where the instrumentation had to work. So down at the lower level, at this minus 640 level, that's where the DCS is. The control system, the $55 million control system, is underground at minus 640. In this case, it's from Foxborough DCS. You can see the rest of it. You're all used to this stuff. We were asked to do wireless measurements. And the main thing is, hey, can we do wireless underground inside these tunnels in support of those applications we talked about 20 slides ago? So I was underground with a radio frequency spectrum analyzer, 2007, doing these measurements. And there are specific frequency bands. 2.4 gigahertz is the one around the world. So a vendor can sell their products in the UK, Tanzania, South Africa, Australia, US, Canada, and they can all work at 2.4 gigahertz. The other places around the world have different frequencies that you can and cannot use. In Canada, they could use 5 gigahertz. Underground, you sort of can use anything you want, but if we're all stuck in open pit or like a mountaintop, you have to live with the local jurisdiction. I want to focus on this part that was down here. Oh man, sorry, it came in as black. Maybe there's a different color. Let's try this. Oh yeah, there we go. So in this realm, this is a spectrum analyzer, so it's frequencies going along the side, frequencies along this axis, and vertically it's amplitude. So if you see these spikes, it basically says, hey, there's some radio signal at that frequency. And we were just looking at what's around there. But gentlemen, we're really talking about leaky coax module pin inside what you're going to be talking about. You already saw this diagram, right? So we saw, like, here's radio propagation inside here. I'm trying to get you the instrumentation in 2011 because this is what the vendors want you to buy. What's this got to do with leaky coax? Leaky feeder, I think is how we called it. Here's what a coax cable really looks like. And you probably have these at your house. It's going, you know, maybe plugged into the back of your TV or something. And it's, okay, it's got an insulator, it's got a shield, it's got a center conductor. So the shield is ground, the inner conductor on the right-hand side, that's hot. So there's ground, there's hot, there's not hot. That's what a cable looks like. Now specifically, there are these things here. This, let's try to color it in, that's a dielectric. It's like a type of plastic or rubber or something. Oh my goodness, he put in equations. What the heck is that? So I know this is what you probably want to give me, is all these negative things here. Oh my goodness. So, you know, you lose, I like the material, you can probably tell. You lose half the people by one equation. We have we have 1, 2, 3, 4, 5, 6 sort of equations. Okay, all of us are now asleep. And I'm sure Paul really is asleep. It's like 2 in the morning for him. He's long gone. So this is on the right-hand side, right over here, we're looking at this cross-section of the coax cable itself. The thing right in the middle, let's change the color. That's the center conductor. And then here's the shield on the outside. There's hot, there's not hot. And what this is showing is, if you change the materials, the dielectric constants, these things work differently. What is he talking about? Well, once again, here's the equation, the guiding equation for a leaky feeder, actually for any coax cable. And you have terms, the resistance of the cable, this thing called inductance and capacitance of the cable. And those factors come into play, and you got modules that are going to highlight this. So if you're a EE or a Chem-E and you're not used to this electrical engineering, this physics stuff, don't worry about it. You got great people that are just pointing out the terms. It says, I could change the material, different materials, plastic, rubber, types of plastic have different values of capacitance and inductance, and resistance tends to be the wire itself. So check it out. If I just choose this, if I choose this particular type of cable, then it's going to have a leaky capacitance. And what that means is the signal leaks out from the actual wire itself. I could do the same thing down here. I can have another type of wire that has the same performance. It's a leaky resistance. Or I could have a leaky inductance. I'm sure all of you are like, what the heck is he talking about? That's what I'm saying. Let's go back down underground inside the uranium mine. In that mine, I took a photo of this particular board. The miners that are underground have a radio system. And the radio system, remember that diagram? I'm going to go back a couple. Come on. One more. That diagram. So let's say that you are down here. You're driving some skiff down here, and you want to talk to one of your colleagues that's like over here. Now, this distance-wise, this is like 1 kilometer, 1.5 kilometers long, and you do not have, there's basically no way that you can get your radio signal right from your walkie-talkie to go down this route and then wind up inside his radio. It's not going to happen. So what the heck, how do you get your communication network to work? Go back. That's leaky cable. So you're going to become experts on, hey, we may use a leaky cable for our communication system. You may have walkie-talkies that have a specific frequency that they use, 433 megahertz tends to be it, and they talk through this crazy cable. So the cable itself becomes an antenna, and you just string this thing all over the mine. So this is the distribution system for the leaky coax cable for this particular mine. And they bought their material from a company called MSA. Maybe you guys are used to that. It was MSA. And it was, okay, so remember how this works. Your radio then talks to this antenna. Multicom, I love it, I love it. So you talk to this particular distributed antenna, your signal gets into the antenna, and then it goes all over wherever these wires are through the mine. That's what it uses. But the whole way, it's also leaking out. So, you know, your neighbor, your friend that's, 200 meters away or 2 kilometers away, whatever, uses the same distribution system, and away you go. What are these boxes? In case you're wondering, like, what the heck are these little boxes here, Peter? Amplifiers. They're repeater stations. Because the signal, it's degrading in amplitude because it's leaking out of the cable. It's leaky coax. So every so often, boom, you jack it up again with one of these amplifiers. It's a pretty interesting way for a distributed antenna, a leaky coax, for your radio system. I got to tell you, this is like 1990s technology. You can do it much better with a Wi-Fi network that's throughout the plant, throughout the mine. And you get voice and video. And John, you're a video guy, man, I'd love it. You would be right on top of this. But you're going to see this is leaky coax. That's how it works. You're going to have a whole module that's specifically on that particular system, leaky feeder systems. What about this other stuff? I know I'm really boring you. So, the reason that they had slack on the cable at their amplifiers because they didn't know. They had to do the installation themselves, John. It didn't need it. There's no specific reason to have those multi-wraps. So they actually had it originally just like up on the walls, up in the roof, and they wanted to put it on a single board. So they ended up taking these repeaters and just put it on one board so they sort of knew where everything was. That's a great question. Yeah, don't you know? Yeah. Yeah, they had their donuts too. What about these other modules you're going to run into? 14 through 19 are dealing more with systems, from field buses into SCADA system. I love this. Once again, like I said, I was in Hong Kong about a month ago running a big SCADA meeting. It was a lot about energy distribution systems. And so you may say SCADA and data. I say SCADA and data. So there you go. There you go. It could be a training station, man. I totally agree with that. What we're trying to show here again is what you're going to find is there are multiple technologies that come into play as your communication system is running. And the communication system can be transporting data from sensors, from instruments themselves. Could be command signals going down to open that valve, shut that valve, whatever. And there are devices in this particular diagram. I'm trying to show, like, here are organizations. Now, this is related to, as you can see, it's more energy related, but the same idea comes into play no matter where you are. There are organizations that are interested in certain pieces in this communication and instrumentation chain. Then on the right-hand side, there are the protocols. I keep hammering this thing, guys, because you got some great courseware here, these modules that are going to say, this is using DNP3. This is using IEC 61850. This particular vendor is using HART. This vendor is talking ISA 100. That one's talking Profibus. This is an instrument that wants to have a video camera. The video camera is going to require, 3 megabits per second, so I have to have a certain type of network that can deploy that. And that is Instrumentation Circa 2011. It's all in the courseware. I really think you're going to like it. SCADA, remember I say SCADA, you may say SCADA. So SCADA systems, a long time ago, they were huge, big computers. It's supervisory control and data acquisitions, grabbing data and doing stuff with it. First generation, big computers. Second generation, distributed. All of it's in the that. Third generation, right here, right now, intelligent electronic devices. And it's IP, Internet protocols, IP to the device. We're going to hit that a lot. And you're going to see a specific, you'll talk at all these human-machine interfaces, HMIs, and you'll look at how HMIs can interact with the instrumentation itself. You've got a great course just on SCADA. This is a generic architecture. Notice, although once again, I grabbed this out of looking over at smart grid or electricity distribution stuff. But this architecture comes into play almost anywhere. It follows a specific model that was developed in the 1990s at a university here in the United States called Purdue University. And it's called the Purdue model. And in the Purdue model, there's a standard that's associated with that, SP95, that basically said, here's how you should architect your SCADA system itself. To talk to the corporate local area network where the CFO and the guys, or men and women with the glass windows out there, the big corner offices, they're up there, and they need to be isolated from the actual activity by that firewall. And you'll see all this in network stuff. workstations are there. They're communicating through all these levels down to actual PLCs, and